calling for considered action, and I'm calling on specifically the U.S. Congress. The setting here is that this asteroid 2004 MN4, and I'm going to call it MN4 because it's simpler, is going to make a very close encounter, unusually close encounter with the Earth in 2029. And that close encounter sets up the possibility of a return. The problem is that in the absence of any assigned responsibility within the U.S. government, there is in fact no one to make major decisions which ought to be made. And part of my argument is that there is one decision which needs to be made within the next year or two, and I'll get to that. Okay, so in summary, as I said, I'm calling on the Congress to address those two things. Number one, identify a professional body to check the kind of work and the logic that I'm presenting here. And secondly, to in fact address the fact that there is nowhere in government today a specific assignment or any real work identified with protecting the Earth from the potential impact of near-Earth objects. Okay, what we're dealing with here is a very low probability event. That's always the case with near-Earth objects until one day when it's not. But probably none of us in this room will be around on that day. Nevertheless, even a low probability event with a high enough consequence is something to pay attention to. You and I do that every day, basically by paying $3 or $4 of auto insurance. The probability of an impact that I'm going to talk about is 1 in 10,000. That is almost precisely the probability that you or I, any day of the week, any day of our lives, will have an automobile accident, a reportable automobile accident. Our insurance, the potential loss is what, $30,000, $40,000. You multiply 1 in 10,000 times 40,000, you get $4 a day. That's about what we pay in insurance. It's smart. Okay? Right now we're driving around in the solar system uninsured. Here's the Earth, not the small dot there, unfortunately, but the big round dot is the Earth. This is the error ellipse in 2029. This is a 2029 close encounter. For those of you who don't know, believe it or not, Friday the 13th of April. And we can tell you exactly where. So this is the path of the asteroid, relative motion path of the asteroid as it passes behind the Earth. I'll put some more references in there. There's the orbit of the Earth and the direction of the Sun. And you can see that it's already curving. In fact, going this close to the Earth, that asteroid, as it goes by, takes about a 28 to 30 degree right turn. Now, what I'm going to do on the next slide, which is the one to really pay attention, picture yourself riding on this asteroid as it comes about to this point. Let me point out that that asteroid, that line, can be anywhere in this 3 sigma ellipse. That's the error ellipse of this particular asteroid. Just one quick word about error ellipses for near-Earth asteroids. They tend to be lines. That is extremely narrow in all dimensions except one, the one along the orbital path. Hence, this looks like a line, and it actually is damn close to it. Okay, so we now are going to go, oh, by the way, there's the geostationary orbit. So you can see that in 2029, that asteroid is going to come inside the geostationary orbit. That's how close it is. It's going to be a visual object. You don't need telescope, you don't need binoculars, just your old eyeball. The line here is the plane of the asteroid as you're riding along. And you'll notice that the plane of the asteroid does not go through the center of the Earth. It goes through the upper half in this slide. I'm going to expand that error ellipse. Here it is expanded. There's the centroid of the error ellipse and some dimensions, which I'm not going to worry about. Okay, here's the next thing. If the asteroid passes not through the centroid, and of course, let me remind you, the error ellipse moves around as we make more and more measurements. Okay? We correct, we refine the observations, and the error ellipse in this slide would slide back and forth and gradually get smaller and smaller until it comes down to a point. The centroid may also move further and closer to the Earth, but it's been bouncing around between 5.7 and 5.58 Earth radii for the last 3 months, so it's relatively stable, and it'll probably stay pretty stable at around 5.6, 5.7 Earth radii. Now, if instead of passing at the centroid, which of course would be some kind of a miracle, it passes at this point, it's going to end up, right now it has a 323-day orbit around the Sun. It would end up with a 426-day orbit around the Sun. In other words, it gets a gravitational kick in the pants. We do this with satellites all the time, sending them out to the outer solar system. We get a kick in the pants from Venus or whoever happens to be close enough, and we can use them. Well, this NEO will get a kick in the pants and will end up, if it goes through here, with a 426-day orbit, over a third larger than it is now, 417 days, 414, etc. That's important because these particular points, if it goes through right at the right place, it's going to come back to the Earth in 2036. In other words, 426 days and 365 and a quarter days, if you just run it through your calculator, it says we have here a 7-6 resonance. In other words, the Earth goes around 7 more times to 2036. It takes, and it takes the asteroid only 6 times to go around. And they come back together in the same place. So each of these, if it goes through any one of these several places I've got listed here, and many others, but these are the critical ones, it will come back in 5, 6, or 7 years. But the one closest to the centroid right now of the error ellipse is the return in 2036, and that's the one I'm going to be talking about most. Okay, now let's expand that point. Okay, here it is down at the bottom. The actual resonance, where 7 years later, not only does it come back to the Earth, but the Earth and the asteroid are in exactly the same place. In other words, 5.6 Earth radii back, all over again. Okay, but if it comes a little further away, in fact, about 885 meters further out. We've changed scale dramatically here. Okay, if it's 885 meters or thereabouts from that resonance point, it hits a keyhole, and when it hits that keyhole, and I'll show the total keyhole because there is gravitational focusing. In other words, if the asteroid passes in 2029 through this keyhole, it will hit the Earth in 2036. The big question is, will it hit that keyhole, or any of the other keyholes, or will it not? All right, if you got that, we're going on.